worry about the end result. We'll just think about what happens when I try to derive when I try to do a force balance on a small volume of fluid that is flowing along a streamline. Like for example, let's say I have a flow with multiple streamlines, okay, and initially it may be difficult for you to understand what the streamline means. You can think of it, if it's a steady flow, it's just the flow pattern that you're going to observe, okay. At any given point in that pattern, if you draw the tangent, that would be your velocity vector, okay. That's how you try to understand streamline. If you take any particular point, okay, let's say we take a particular point, and with a chosen origin, let's say this point is at a distance s from the origin. The distance measured along the streamline is s, and at this point I'm going to draw a two-dimensional control volume, okay. So this point itself is at a distance s, and I'm going to say this control volume is two-dimensional, so I am considering a 2D flow, okay, and in that flow I am adopting a streamline coordinate system, s comma n, streamline coordinate system, and from a particular origin, a given point P is at a distance s from the origin along the streamline, along the thread, and this control volume here, okay, let's say it has a width of delta s and it has a height of delta n, and you do know that the normal direction is always perpendicular to the streamwise direction. This is s cap and this is n cap. Okay, I have a fluid that is at a that is along a streamline, okay, and I have gravity which is vertically down always. Whatever happens, however you choose your coordinates, gravity doesn't care, it's always vertically down, okay. So I'm going to take this little control volume, okay, I'm going to draw this again here, okay. Imagine it's like a rectangle with side of delta s and a height of delta n, okay. If I say the pressure at this particular point P, if the pressure at that point is lowercase p, the pressure on this face here, I'll call this face 1 and this face 1 dash. The pressure on face 1 would be the pressure at P plus the rate at which pressure changes along S, okay, along S multiplied by the distance that we have traveled. So from the point P, this face is at a distance of delta S over 2 and the other face is delta S over 2. So I have delta P over delta S times delta S over 2, okay, plus higher order terms, and the pressure in phase 1 dash is the pressure at P plus delta P over delta S or partial P over partial S times this point here 1 dash is behind P, so I am going to say minus delta S over 2. Minus delta S over 2. Alright. So if I do a force balance on this control volume along the streamwise direction and perpendicular to the streamwise direction, I want to do a force balance along the streamwise direction, and this should be equal to the mass contained in the control volume times the streamwise acceleration. This is Newton's second law. Force equals mass times acceleration. This force, if it is along this s cap direction, this acceleration is also along the s cap direction, streamwise direction. that are acting along the stream bias direction. That's my objective here right now. Okay. So what do I have? I had pressure on this face here. We always know that pressure is compressive and normal. So I am going to write P1 times the area of face 1. Okay, and it is pointing the other way, so I'll add a negative sign here, pointing the other way to stream, to the S cap direction. And then I have the force on this face 1 dash, so I'll write the pressure plus the pressure on face 1 dash times the area of face 1 dash. Okay, that is only due to the pressure force. Now what about gravity? What about gravity? This entire volume here. This entire volume here. What would be the weight of that fluid? So if I write plus the force due to gravity is equal to, what is delta m? Delta m will be the density of the fluid times the mass contained in this two-dimensional control volume, which is delta V times As. Okay. Now what is delta V? Delta V is the volume of the 2D control volume of sides delta S comma delta N. That is, delta V is delta S comma delta N. In 3D, volume is L cube. In 2D, volume is L squared. It's area. You just have the concept of area. That's what is volume in 2 dimensions. Okay. So I have here delta V. So what I am going to write is that rho times delta V times As is rho times delta S times delta N, and then As, I just derived it previously, is the partial over S V squared over 2. Okay, that is the right side. And I also have minus P1 delta A1 plus P1 dash delta A1 dash, which is minus P1 minus P plus partial P over partial S delta S over 2 plus a bunch of terms times delta A. What is delta A? Delta A would be delta N, and in 3D area is L squared, in 2D area is length. In 2 dimensions, whatever is length becomes area. Or if you are not comfortable with this type of thinking, you can imagine that this volume is sticking out of the plane of the paper, so that you can imagine a width W, and that W would appear here as well as here and eventually be cancelled out. So I am going to write delta N. Okay, and then I have the second term P minus dP over ds delta S over 2 plus and so on delta N. So if I simplify this pressure is going to go away. The second term is going to add up. This is minus dP over ds delta S times delta N. Delta S over delta N. Okay. So what do we have here? We have this term, we have this equation. The first 2 terms these two terms is basically this term here. If we simplify it, we get minus dt over ds times delta s times delta n, okay, that's this term, plus the weight of the fluid which we haven't written down yet, which we'll write, equal to the density times delta s times delta n times the acceleration partial s over of v squared over 2. Partial s of v squared over 2. Now Fg, I'm going to write this is minus gamma or minus rho times g times sine theta. Sine theta is basically if you take this direction s, okay, and if you take the vertical direction to be gravity, okay, sine theta is the angle between the streamwise direction and the horizontal. It's basically the direction between the vertical and the streamwise direction. So this would be S cap. Okay, it would be the direction between G and S. Okay. You don't have to worry about sine theta. We are going to come up with a simplification that will make it easier. So you can write sine theta, I'll just state it, minus rho g partial z over partial s, where z is the vertical height. That is, its height measured along the direction of gravity. Along the direction of gravity. Okay. So what we want now is to piece these together, and we are going to derive a very powerful equation. Okay. So let's put all these together. I have minus partial b over partial s times delta s times delta n, okay, plus Fg, and Fg is minus rho g. I forgot to add, it has to multiply it by the volume, delta s times delta n. So I have minus rho g partial z over partial s delta s delta n. Okay, and then on the other side I have minus rho g times, minus rho times, I'm writing this term here, minus rho times delta s delta n partial s over v squared over 2. Now I took this control volume of volume delta s times delta n, which is a finite volume. So what that means is it's not zero, so I can strike it down throughout the equation. I can strike it down throughout the equation. So what am I left with? I have rho times the derivative with respect to s of v squared over 2, that's here. I'll bring the other to that side, plus partial p over partial s plus rho g partial z over partial s, and all this should add up to 0. What this equation is, this is a force balance along the streamwise direction at any point. This choice of P is arbitrary. Okay? In the final equation, this is in a differential form. It's a differential equation, that means, and it is independent of the choice of P. Okay? So that's very important about this statement here. Okay? It's very important about that you can be at any point, and this would still be applicable as long as that point is along a streamline. Okay. Now we want to do the same thing. Okay, along the normal direction. We want to do this along the normal direction. We want to apply a force balance and write this equals mass times acceleration along the normal direction. Now that is another derivation that we can go through, and it's exactly the same principle, except the component of the force is going to be different. Okay, so what we'll write is, we're going to save some time. I'll remove everything that's not essential. Okay, we'll write this force balance and skip ahead to the part where we have the normal component listed. Okay, so we have minus rho g times the partial derivative of z with respect to n. Okay, that is one part. That's the force due to gravity, minus the rate of change of pressure with respect to the normal direction. And remember, the normal direction is this. Okay, that is equal to rho times v squared over r. So if I rearrange this, I have partial p over partial n plus rho g partial z over partial n plus rho v squared over r equals 0. So this is the normal component, and this is the streamwise component. Streamwise, normal. They are applicable at any point along the flow. There is no restriction. So they are applicable for any point on a chosen streamline. Okay, you can apply them at any point, and also you can integrate them. You can integrate the two relations between any two points along a streamline. You can integrate them between any 2 points along a streamline. One point could be the origin, the other point could be somewhere here. That's one example. One point can be an arbitrary point here, and the second point could be here. Or one point could be here, and the second point could be here. Anyway, you cannot integrate between this point and this point. That's not permissible. Why? Because those 2 points are not on the same streamline. If the 2 chosen points are on the same streamline, that's good. It's like you are taking the I-40. You can integrate between Memphis and Little Rock. You cannot take the I-40 and integrate between Memphis and St. Louis, which is on the I-55. So you need to be careful that you are integrating between 2 points that are on the same streamline. Okay, that's number one. and you should properly integrate this equation between point 1 and point 2, between 2 points. So you should consider the velocity, pressure, height, density at point 1, the velocity, density, pressure, height at point 2. Likewise, you should consider the variation of pressure along the normal direction. You should consider the local radius of curvature and local velocity. So all these will be important. So what we are going to do is try to remove all the unnecessary aspects that we have now passed. We are just going to write the two equations along with a picture that tells you how to use them. Okay, so here is point P, here is S cap, here is N cap, and here is the definition of distance along the thread or along the streamline. So for the streamwise component, we will write it partial P over partial S plus rho times partial S over V squared over 2 plus rho G times partial Z over partial S equals 0 for the streamwise component. For the normal component, we have partial P over partial N plus rho V squared over the radius of curvature, okay,